I'm Dave Markle. I've been in this field of lithography for, I guess, 40 some odd years. Started in about 1970. At that time I was working for a little company called Perkin Elmer. And my boss was a fellow named Harold Hemstreet. He wanted to make more than one of something. At that point we were the electro-optical division, and we built satellites and telescopes that went into space and all kinds of things for the military and NASA, and it was usually just one of a kind. And we started on the development of the first Micralign system. It was a ring field optical system combined with a scanning system, and it started lithography on its way. It took us about 9 months to build our first prototype. We exposed some wafers, we took them in the field. The marketing people said that the customers that looked at those wafers said, "This is the worst photoresist result that we have ever seen, but if you did it using a projection system, that's exactly what we need. You need to improve your resist technique, but the basic method behind it is very sound, and we'd like one of those systems." Well, to make a long story short, in 2 years, Perkin Elmer was building about 30 of those machines a month, and they had great trouble keeping up with the demand. And of course, that made it possible to make big chips with a reasonable yield, and the industry simply took off after that point in time. It made possible the manufacture of small computers on a chip, and of course that led to larger computers on a chip, and eventually we have what we have today. I think the challenge that we have today is that we're approaching a brick wall in terms of the resolution that we can achieve. 193 has gone to immersion. We're doing everything we can with the mask itself, and we're fast approaching the point where there's just essentially no more ways of getting more resolution out of these systems. We are gambling big that a very big step in changing the wavelength will gain us a few more generations, and that's the step to EUV. In fact, that's changing the wavelength from 193 nanometers all the way down to 13.5 nanometers. That's about a 15-to-1 change. And of course, when you make that kind of a big change, you're taking a big risk. I think people are taking a hard look at EUV. There are proponents and people who think that maybe that's a mistake in the making. And generally speaking, they haven't changed their position very much from the last time I got together with them. I think we're becoming polarized as far as EUV goes. You know, the deadlines continue to slip by, EUV introductions and so on. And I think there's more and more concern as we go along that maybe it won't work. But there's a lot of people who are deriving their livelihood from EUV, and they're very reluctant to look it in the eye and say, gee, you know, this really could fail. I think one of the problems in the industry is that big companies tend to want to invent everything themselves. And I think that's a big mistake. And it makes it very much harder for a little company with a new idea to get it adopted in a big company that already owns the market. One of the little startups I'm working with is a company called PSI, Periodic Structures, Inc. And they're working on something that's been used in the microscope field. In the microscope field, very often you want to study live amoeba and so on. You can't use EUV or deep UV because that kills whatever thing you're working on. You can't use electron beams. You're really forced to use visible light. And of course, that brings with it diffraction limits that are quite a bit above the structures that you want to see. And the microscopists have stepped around this barrier by using stimulated emission. Essentially what they do is they stain it with a fluorescent compound, which is caused to fluoresce by one wavelength and then prevented from fluorescing by a second wavelength. And by adroit use of these two wavelengths, you can achieve a very big increase in resolution, well beyond what you'd expect from the diffraction limit. Give you an example, using visible light, they have managed to achieve resolutions as small as 6 nanometers, which is truly remarkable. That's way, way below a quarter wavelength, which is the usual limit. I think the same technology can be applied to lithography by having a resist that's exposed by one wavelength and then inhibited from exposure by a second wavelength. It's really that simple. But we have just started applying this to lithography. There's virtually no money to develop the resist, and it's going to take us a long time unless we get some support that allow us to develop the resist, which will then lead to the equipment that's necessary, and then tools that will allow us to extend the resolution of lithography, perhaps using visible wavelengths. The most important message I have is that we're starving the development of new ideas, and some of these new ideas are really terrific. The best is yet to come in lithography and inspection, where I know a thing or two, and probably in every single area. And we are inhibiting the development of these new technologies by our structure and by our reluctance to go outside and look at new ideas. I think that if there's a message I would like to deliver, it's that we have to change that aspect of our business, or someone else who is more flexible and more open will replace the big companies that we have in this industry today.